This is the walkthrough for the Waves Lab. And before you do anything, you want to make sure that your accelerometer on your iLab device is calibrated to the computer that you're using. So just like how you go to calibrate your force sensor, right? The only other option you have for calibration is this other one that says Excel and two other things. So Excel stands for the accelerometer, and it'll calibrate two other things as well that you won't need right now, but it both does it at the same time. So you go through that if you need to. Now you're going to go through 5 different trials in this part. Right? So simple harmonic motion. One example is a mass on a spring. So for our mass, we're going to be using the iLab device. All right, and then you have 2 springs. One is stiffer than the other. One is a little bit looser. So we're going to attach, for the first trial, we're going to attach the stiff spring to the force sensor on the iLab device. So this will be our mass on a spring. Okay, so we'll go over to our software and we'll click on the accelerometer sensor. We're only going to be looking at acceleration in the y direction, so we can go ahead and uncheck the AX and AY boxes there. Right, and so to begin with, we're just going to click record. We'll pick up the iLab device by the spring, and we'll just let it bob up and down several times. And you see we'll get a nice sine wave there. We'll just let it go a bunch of times, and then we'll stop. Okay, so you want to take a screenshot of this for your lab report. And then we're going to go ahead and zoom in on a couple of the wavelengths. All right, so from this, you're going to want to determine the period of the wave. All right, so remember that a period of a wave is the time that it takes to complete one full cycle of the wave. All right, so one example of that is from crest to crest. All right, so we'll use our data tool and we'll click and drag from the top of one crest to the top of the other. And remember up here we have this delta t, our time interval. So that tells us the period of the wave. Now the frequency of the wave is not displayed on this graph, but you can actually simply calculate that by taking the inverse of the period. All right, then for amplitude, remember amplitude is the distance from the equilibrium position to the crest or to the trough. So equilibrium is your halfway point between crest and trough. Okay, then we're going to go ahead and do a Fourier transformation. So if you go in the toolbar here, and the second drop-down menu is FFT. That stands for Fast Fourier Transformation. So we'll go and we'll click on the bottom one, the 4096. And then when you put your cursor over the graph, notice what happens. We have this graph display down here, and there's a sharp peak. Okay? And when I put my cursor right over that peak, over here, it'll tell me the frequency in hertz. All right, so I have to make sure the cursor is over that when I'm reading that. So I'll see my frequency is 1.194 hertz, and that should be pretty close to what I calculated when I took the inverse of the period. Okay, but this will just be a little bit more accurate because it's the computer that's collecting and reading all the data itself. Okay, and now you go on to step 2. You're basically going to repeat step 1, but this time with a larger amplitude. So to get a larger amplitude, what you did the first time was you just picked the device up and let it bob. To get a larger amplitude, you can go ahead and pull the iLab device down, and it'll have a bigger bob. And one thing to pay attention to in real time as you watch the device bob up and down is as it's bobbing up and down, look at the graph and notice what portion of the graph corresponds to the iLab at its highest point and what portion of the graph corresponds to the iLab at its lowest point. Okay, so that's something to think about, and that's one of the questions you'll see in your report as well. Now, trials 3 and 4, you're going to repeat what you just did, but with the looser spring. And then your final trial 5, you're going to see what happens when a mass is suspended, a different mass is suspended from a spring. So we'll go ahead and use our stiff spring again, and instead of the IOLab device being our mass, we're going to use the metal cube that we used in the last lab. Okay, and then we'll just repeat what we did before. Let it bob up and down, collect the data from the accelerometer, and you'll determine your period, frequency, and amplitude again. Now the last part of this lab is going to use the microphone sensor. So if we go over to the software, we'll click reset a few times to clear the screen, and then the microphone sensor is right down here. Now you don't have to calibrate anything to use this. You don't have to worry about putting the microphone real close to your mouth or anything. So for instance, you can click record and you can see it's already collecting some data. So I'll click stop, and I'm going to take my zoom. I'm going to do my left to right zoom, and I'm going to click in and zoom in on just one little portion of the graph. Okay, I'll need to zoom in a little bit more, and now you'll see we're starting to get a pattern. Okay, it's not as pretty as a nice sine wave from the simple harmonic motion, but this is what the human voice looks like. So your goal here is to get the frequency of your voice. So again, we'll go back to the Fourier transform. When I click on the 4096 and put the cursor over the graph, it's kind of hard to see like a striking peak. Okay, I think maybe there's one here, but you can try other settings of this FFT. So I'm going to try the 256, and here now we're seeing there's several clear peaks, right? There's one here at about 112, 243, all right, big one there at 599. So which one is the frequency of your voice? Well, it's generally the lowest one. So remember that the human voice for men ranges from about 70 to 250 hertz, women from 100 to 500. So for me, between 70 and 250, right, I'm going to say, well, I don't really have a high-pitched voice, so this 243 is probably not it. All right, it's usually the lowest one. That's your fundamental frequency of your voice. The rest of these, we call them formants when we're talking about the voice, or these are the harmonics of your voice. So that's what makes the human voice unique in some ways, is that it's not just one pure tone like a tuning fork, but it's several tones combined together. And you'll use the fundamental frequency of your voice to determine what musical note is most closely associated with your voice, and you can do that by comparing the frequency of your voice to what the frequency of other musical notes are. So there's plenty of charts online that tell you the frequencies that are associated with different notes, and you can find out the note of your voice from that. And that is it for Lab 5.